Hi folks, Mr. Ackerman here. Thanks for watching. This is the supplementary video for Unit 3, Lesson 3, where we start to talk about how gravity, one of the fundamental forces, leads to circular motion. And the interesting part is going to be when we talk about orbits of planets around stars, and then later orbits of stars around the centers of galaxies, and we get into a discussion of dark matter. But all of that comes a little bit in the future. First, we're going to start with the basics. So I'm going to take you to the course pack to begin. You're going to see we're in Unit 3. You're going to scroll down and find us in Lesson 3 here. You're going to see that there's a video, Newton's Law of Universal Gravitation. That's the video that goes with this video that I'm making for you right now. The questions to try in the course pack they're listed in the unit schedule rather, are ones that relate to the textbook that you see here and also that you see here. Now, there's a second part to this lesson, which is about something called dark matter. There's a separate video for that, which is actually made by the Perimeter Institute in Waterloo. I think you're really going to enjoy it. The link is to YouTube in here, so that's not what I'm talking about just yet. That's going to come next. But when we do that, you're going to see a course pack page reference with some practice problems, and that's when you're going to do these. So just a reminder, once again, for now, all we're dealing with is this video of mine. This is the supplementary video for that. The practice problems are all in the textbook, and so let's take a look at G-class to find out what things are going to look like there. You're going to notice that there are two sets of lecture notes. One just says Lesson 3. That's the one we're doing right now. The other one on dark matter is coming up in the future. The video you're watching after you watch this will be Newton's Law of Universal Gravitation, and you're going to ignore the mystery of dark matter for now. It's coming up in the future. Okay? So, assuming you've downloaded this and you're watching this video here, here's what you're going to see in your lecture notes. I'm just going to pull myself to the side for a moment so that you can pay attention to the lecture notes a little more clearly. There we go. So the first slide here is just really a refresher on Newton's universal law of gravitation. I go over all of this in the video, and a lot of you know it from last year. So there's really nothing new happening here, but there's some interesting stories about how this law of Newton's was used to discover some planets that have never been seen before. So pay attention to the discovery of Neptune and Pluto when you're going through that. On the next slide, you're going to see a practice problem that's in the textbook, and since it's in the book and it's, I believe I talk about it in the video, or if not, something very similar. I'm not going to spend a lot of time here because you can look that up in the solution manual, or you can message me if you're having trouble. Same thing going on here on the third page of the lecture note. Now, you may notice something seems a little weird here. It says the force of gravity equals the force of gravity. What the heck does that mean? Well, we have two ways of writing the force of gravity. One is the general way in Newton's law of universal gravitation, and the other is the way that we often use if we know the value of g at some point in space. But since they both represent the same thing, we can write gmm over r squared equals mg. That's what I mean when I say the force of gravity equals the force of gravity. The m's cancel, and you get a formula for our good friend little g, the gravitational field strength, or the gravitational field intensity, or the acceleration due to gravity, whatever you want to call it. And that's used down in this question here when they talk about the acceleration due to gravity on Jupiter, right down there. So I think this particular slide is not in my video, and that's why I just wanted to go over what that meant. Anyway, moving on, we're going to get into some two-dimensional vector examples because forces, as you know, act in 1, 2, or even 3 dimensions. So this is a two-dimensional example. Since it's 2 dimensions, you're going to be using components. This practice problem is done in the video, so I'm going to leave that to you. And here's where things really get interesting. This is when we start talking about satellite orbits. So we're going to be talking about uniform circular motion. Pay attention to this one. This is a really important problem which sets the tone for the remainder of the lesson. Okay? Again, this is done in my video. So one last thing before we wrap up here. The 6th page of the lecture notes has this graphic here. This is kind of an interesting one here. You've got Earth and a busy looking diagram, but if we just zoom in here, see if you can decode this. I'll tell you a little bit about it, and then you try to figure out the rest on your own, because this is not in the video, so it's going to be a good thinking exercise. They show on this axis time, or orbital period. And then on this axis, they show the height above sea level, and it's in a weird unit of measurement, capital MM, so not meters, not kilometers, but capital MM, and since you guys all know your metric prefixes, I'll leave that to you to figure out. They also have miles, in case you're interested. On this axis is the orbital speed in miles per hour or kilometers per hour, and you could of course convert to meters per second so that your calculations are a little bit easier. Finally, on this axis, we have the radius of the orbit. Now, you should distinguish between that and the height above sea level. Sea level is, of course, right around here, but the radius of the orbit, where does that come from? Think about that, and then you'll understand why the numbers are slightly different on these two axes. Just looking to the side here, there's one other graphic, which if we were together in class, I would be talking about with you. Satellite crowding. It's a diagram or picture of Earth with all this stuff around it. Each of these points is meant to represent where some satellite is located around our planet right now. As you may or may not know, there's lots of different satellites up there. There's communication satellites, there's weather satellites, there's spy satellites, there's scientific satellites like the Hubble Space Telescope and others. There are so many of them that there's a worry among scientists that if one were ever to suffer a collision with another one, it would instantly splatter into this debris pattern of very fast-moving particles. And if one of those struck another satellite, which then exploded, then you kind of have this cascading effect, almost like a chain reaction, where one disaster leads to another. It's conceivable that the Earth could end up kind of blanketed in this orbital debris field, making it almost impossible to launch future satellites. So that's what this is all about, and if you want to look into that, it's kind of an interesting potential problem that we're having to deal with as we venture further and further into space. Anyway, that's it for now. After you finish this, you're going to go and watch my next supplementary video, which will guide you through the dark matter portion of the lesson, which is where things get even more interesting. Thanks for watching, hope you're doing well, and have a great day. Bye for now.